Let's see how we can perform deletion from a heap. And as before, let's now go over the principle step by step, and then we also switch to the visual illustration as needed. And our job is to really delete the root. So whenever you want to do deletion from the heap, as I said before, you cannot delete any arbitrary node in the from the tree. By definition, you can only delete the entry with the minimum key, which according to the relational property is going to be the root. So whenever you want to delete a node from the heap, it's gotta be the root with the minimum key over here. That's something I want to reiterate first of all. And the heap, of course, is a complete binary tree, so it has a height h. How do we do that? We got two main steps as in the insertion. So the first main step will be we want to delete the root, and this may temporarily break or compromise the heap order property, which is okay, as long as in step number 2 we will restore the relational property or the HOP. It will be okay. Let's see how we can do that. For step number 1, we're going to have several sub-steps to really achieve the deletion. We're going to let the rightmost node at the level h to be n, right? Now notice that the step is kind of similar to how we had to do for the insertion, but not exactly the same. Let's say we name the rightmost node to be n. Let me just do that right away. Let's say this is the same heap that we dealt with before, but now we want to remove the root. And the rightmost node is over here at level h, and let's call that n. Over here, this one here, let's call it n. This will be at level h, the bottom level. And the next one, we want to replace the root's entry by n's entry. How do we do that? Well, let's do that right away. You can see this one here is 13w, right? And we know that eventually this node has to be deleted. So this entry is no longer necessary. So that's why replacing the entry over here by this will be okay. But we're going to delete the node in a moment. So what we'll do is we're going to cross this out, and then that one there is going to be replaced by 13w. That's the replacement. All right. And 1.3 will be we want to delete the n. And how do we delete this particular node over here? Well, even though the tree is not really a binary search tree, but according to what we learned about deletion of the binary search tree, which case is this? So this is more like deleting a node without any child nodes. Though it's more like a case number 2, I believe. You can double check. Right? So we just delete that. And to delete it, what we will do is we're going to maybe just set this particular reference over here to be null. And then hopefully this node here will be garbage collected at some point later. Right, so that's about step number 1. And the consequence will be from step number 1.1 to 1.3, we have successfully maintained the structural property. Well, if you think about it, what we are doing is we know that we wanted to remove 4c. What we do is instead of deleting the root directly, we simply replace its content by the rightmost node over here, and then we simply delete it. And since we're deleting the rightmost node, at the bottom level h, we are still filling out the nodes from left to right. That property there has not been compromised, so it is still a complete binary tree. It will be important to actually say this. So this part over here about deletion, at level h, the nodes are still filled from left to right. So that means the structural property is actually maintained. That means complete binary tree still. That'll be important to note right away. At level h, and then filled from left to right, so that means we still have a complete binary tree. That's step number 1. Hopefully you're okay. However, after step number 1, we may have compromised the other property about the heap order property. How? Well, let's take a look right away. For example, if you look at this particular node here, 5 larger than or equal to 13 is definitely false. So that means I have already violated the relational property after this replacement. So we have to fix it. And we have to fix it from the root. So that's why rather than doing up heap, rather than doing up heap bobbling from the bottom. Now this time we have to do the so-called down heap bobbling from the root, right? That's where the name comes from. Number one, you want to notice that after the replacement, it's very likely that you have violated the heap order property, either to the left child or right child or both. In that case, you will actually have to do some restoration, which is something we're going to do in step number 2. All right, let's take a look. And we want to restore the heap order property using the so-called down heap bobbling. That's something we'll do. So we go from the root, and possibly in the worst case, we're going to go all the way down to the bottom level, level H. And let P to be the root, right? Let's now name that right away. So P will be, for according to our convention, will be the parents. So let's say the root over here is going to be just P, right? We may have to swap P and C later. And while the heap order property is not really restored and P is not external, you can think about the worst case would be if you have to go all the way, for example, down to this particular path. In that case, ultimately, when P becomes external, in that case, there is no further child nodes for you to compare to check the relational property. In that case, that means we have already restored all the heap property above. In that case, we are done, right? That's what that line really means. And if P has no right, okay, so this is about how we can set the C, right? Remember, we got P and C, like in the insertion case. We already fixed the P to be the root to begin with. What should be the C? So there are potential, 2 potential nodes to be the C, either this one over here or this one over here, right? Let's now see. According to the principle, that's what we have to do. If the P has no right child, in that case, it must be the left child, meaning that we have no choice, hypothetically, right? Let's say we are here. Let's say here, we have one node over here, but we don't have any node over here. In that case, you have no choice but to choose this particular node. Otherwise, in this case, if you got both child nodes over here, in that case, what should you choose? Well, according to the principle, we're going to choose the C to be P's child with a smaller key value, right? That's what we're going to do, right? According to this, let's see here, I need to choose either between 5 and 6. Which one is smaller? Apparently, this is smaller, so that means this part over here should be the C, right? Hopefully you're following so far, right? And then we're going to also check to see, according to P and C, the parent and the child, is the heap order property maintained? If it is, we are done. If it is not, in that case, we have to swap the 2 nodes. And we're going to keep doing this until we actually restore the heap property or we actually reach to the bottom level, either way. All right. And so we are basically moving downwards along a root to leaf path. That's something you will see visually in just a moment. And that's about the steps. And then we're going to talk about the running time at the end. Let me just complete the illustration over here. Let's now try to do downward, down heap bobbling. Let's now compare the smaller child over here, 5 and 13, right? So what you really want to write down will be 5 larger than or equal to 13 is actually not the case. So that means we have to swap these 2 nodes, right? And you pretty much know how to swap them. So let's now do them. Let me use purple here. So swap these 2. So 13W is going to be here, and the 5A is now the root. All right, and then let's change the reference for P and C as well. So this one here is no longer here, and this one is no longer here. So this one will be the P after the swap, right? And in order to choose the C, we have to look at the 2 child nodes, right? You can see you got both child nodes. That should be the else part. In that case, we should choose a smaller one. 15 versus 9. Which one is smaller? Apparently, this one is actually smaller. In that case, we're going to compare whether or not, let me just put a C here. So this will be the child nodes over here. And if you try to compare the key value, that will be 9 and also 13 over here. Right? Let me just do a little bit better. Well, let me use highlighter. I think that might be easier for you to see. So we got 9 and also we got 13. Right? Let's now write down the heap order property that we have to check. We're going to check to see whether or not 9 is larger than or equal to 13. Apparently, it is not the case. So that means the relational property is still violated at this level. So we have to swap the node. So we're going to do is we're going to swap the nodes. And swap this and also swap this. So this will be 9F. And this one here should be 13W. Right? Hopefully you're okay so far. And then after this, we also have to change the reference for P and also C. And this will be the latest one we want to take a look. That will be the P. And how do we choose the C? Since you got two child nodes, we have to choose a smaller one, the ones with the smaller key. 14 versus 12. Apparently, 12 will be the winner, so we choose that as a C. And we have to now check to see between the P and C over here, is the heap order property maintained? So we have 13 versus 12. Apparently, it is not. Why? Because if you try to write it down, the 12, the key for the child, larger than or equal to the key for the parents is not the case, right? 12 is not larger than equal to 13. And then we're going to swap them again. How do we swap them? So swap this and swap this. So this will be 13W. And this one over here will be 12H. I'll put it here. 12H. Right? And you can see now we can update the P and also update the C. And P is already over here, and this is some external node. Meaning that we can now terminate the process. There's no more checking to be done because it's already external. We only check for internal nodes. Alrighty, let's now see. Well, overall, you can see the root to leaf path that we have done. Over here, you can see here we got here, here, and here. This is a single root to leaf path. And the mechanism is called down-heap bubbling. Right? It's very important for you to understand the terminology. Down-heap bubbling. Root to leaf, as opposed to leaf to root. And the resulting tree is something like this. Let me just also highlight the result. We got 5A, we got 9F, we got 12H, and also we got 13W, right? So these are the resulting tree, the nodes in the resulting tree. And only this particular path is impacted according to the algorithm. And we don't need to really prove about the correctness of the algorithm, but you should really think about why the resulting tree is still a heap. We can check very quickly. You can see the 5 over here is smaller than or equal to both the 9 and also 6, right? And also this part over here, you can check very quickly. That's also a heap. And let's go for this way quickly. And if you look at the 9 over here is smaller than 15, smaller than also the 12 over here. So that's also satisfying the relational property. And this part here, the heap property is unchanged. It's still satisfied. What about this part over here? And for this part here, 12 is less than 14. 12 is less than 13 as well. So the entire tree is still a heap. So little exercise for you. Also similarly for insertion. Little exercise I'll put down here. The exercise would be, is the resulting tree after deletion still a heap? That will be something for you to check, and we show to you how to check it. Alrighty, let's now go back to the slides. And what will be the running time? Well, the running time obviously will be, since for every iteration for the while loop, we're just doing some swap and some if conditional check. That will be just big of 1. How many levels do we have to go down? Well, in the worst case, we have to go down all the way from the root down to an external node at a level H. So the number of swaps that we may have to do ultimately will be, in the worst case, big of H for log n, because the tree is complete. Right, so you can definitely look at the line over here is really just corresponding to the conceptual steps over here. I think that the conceptual sketch here is very close to be adapted to Java code. That's something up to you. you should really do the exercise beyond the lecture for your learning. And it will be executed for big of h or big of log n times. So that's why overall the running time will be log n. All right, so that's about deletion, and you can see the way we actually try to restore the heap property, as specifically the relational property after insertion or after deletion is pretty symmetric. In one case, you try to go go downwards. In the other case, you want to go upwards. You want to know which one is which for sure. That's about the two fundamental operations we want to cover for the heap. That's enough because we talk about how you can access to the root and also how you can insert, how you can do deletion. And the next one will be how we can construct a heap from scratch.